Hello everyone, my name is Timothy Lee Grant. So today I am going to do a little bit of a different video. I normally do my software engineering projects, so my JavaScript backend server, but today I am doing things a little bit different. I am going to be trying to kind of document how I'm going about and studying for Leetcode. So I tried to change up my process, and in the past what I would do is I would try to do problems, and I would just try to do a problem and then I wouldn't fully learn it. Okay. And then I would just go on to a new problem. And this method was very inefficient. So I'm trying to kind of document how I am going about and trying to learn Leetcode. And so this video actually might be kind of boring. I don't know. I've been doing this Leetcode map. So I've been doing like 2 pointers and sliding windows. I think I'm going to come down to trees and learn a new topic, okay? And kind of document the process of how I'm going about starting a new topic. So with this trees, I'm coming over here. So this is kind of the map that I'm following. But then I'll go down here to the trees, okay? So then let's just go to an easy, and I might need to, it says that I already did this one, so maybe I'll need to press the little restart. Oh, no, it's already with nothing in there. So I'm gonna just get my notebook right here and start trying to introduce myself to trees. So as you saw on the Leetcode path, or on the Leetcode problems, I've actually done some of these, and I think I looked at trees a long time ago, but now it's time to kind of go through them again and using my new method. So which one is, this one is the water. I have two identical cups. One is coffee, one is water. So I was like, which one? Okay, this one. All right, so let's see, same tree. So given the root of two binary trees, P and Q, write a function to check if they are the same or not. So what I'm trying to do right now is I just started trees. So I picked an easy. I'm trying to figure out, okay, do I even understand? Like, I'm trying to figure out, what is the lay of the land? What is this problem, or this type of problem? So right now what I'm seeing is, okay, here we have trees and it's like a node, right? So we have a node and they have a pointer to the left and a pointer to the right, okay? And I remember for trees, there is like in order, pre-order, post-order. And I know that you traverse through recursion. So these are some of the things that I remember from a long time ago. Now I'm going to try to just introduce myself to this topic again and make any notes that I have. So I'm going to write this down, like 100 same tree, okay? So now, two binary trees are considered the same if they are structurally identical and the nodes have the same value. So immediately what I'm thinking is I'm just going to try to traverse the tree and look at each node. I'm going to try to go to each node, and I am going to return false if any of the nodes are not the same. Okay, so let's try to figure out how to do that. Is the same. Okay, so how are we going to traverse this recursively? So traverse and then we have P, and we have Q, okay? So now I need a helper function, traverse. Do I need like self.traverse? I don't know. We'll try it out. Traverse, and then P and Q are going to be P and Q. Okay, so now this is going to be like node right there, right? So let's see. If P dot value does not equal Q dot value, return false, okay? So I'm going to be passing in this node, and I'm going to be passing in this node, and if they're not the same, I'm going to return false, okay? Also, I want to say, like, what if this one didn't exist? So we have P, and we don't have Q. So if not, how would I capture that state? So, if not P and not Q, so if both of them are non-existent, right, return true, because that case both of them don't exist. Then what I can do is now say if P, return false, okay, if Q, return false. And the reason for that is because I already checked, like if they both don't exist, then we return true. But if P exists, that means P exists and Q does not. Otherwise, we would have hit this case that both of them don't exist. Okay, so in this case, P exists, but Q does not. And then in this case, Q exists, but P does not. Okay. So now, then we check if at this point right here, we know both of them do exist. So I can check their value, because I was concerned about, like, if I said value right here and one of them didn't exist, well, then I'm going to get an error. But now we're okay with this. So now what I want to do is, did I hit all of the base cases? So what are the base cases? The first one is like, so when traversing, I want to go when you pass in the element that's not there, right? So traversing a tree is, I keep going until I hit a null. So if both are null, if one of them is null, yeah. So I've hit all of the base cases. So now I can traverse like P dot left and Q dot left, traverse, and then P dot right and Q dot right. So now I'm going to be going down this path and then spreading myself all the way down. And then I'm going to pop back up, okay? And then I'm at this 2. And then at that point, I'm going to get back some result. So result 1 is equal to what it comes up here, okay? And then result 2 is equal to this traverse down the right path. And now if I find any falses, I want to pass that false up. So I want to say return result 1 and result 2. So if result 1 is false and result 2 is true, then this entire thing evaluates to false. If this one is false and this one is true, the entire thing gives false. If this one's false and this one is false, then it evaluates to false. If both of them are true, that's the only case that this statement right here will evaluate to be true. Okay. So now can I just do that? Let's press it. Okay, so it didn't like it. Let's try to figure out what's going on. Traverse is not self dot what is that? Okay, so now it wants self. Okay, wrong answer. So now this indicates that there is some lap in my knowledge, right? So I'm going to try to figure out what I did here and what is wrong with it, because I think it should be right. So now this is good news insofar as like I'm able to take this problem and investigate like, okay, cool. What is the lapse in my knowledge that I'm experiencing right now? So, and it came out to be false. If both are not the same, okay, if one of them exists, or if the values are not the same. I don't think this would make any difference. No. Left, left, right, right, P, Q, P, Q, okay. All right, well, so the other thing that I now do is I no longer try to stress out, like if I don't figure something out, I go right to the solution. So I'm not trying to prove that I'm so smart and I can just figure it out. No, I'm just trying to understand it. If both are null, then we return true. If this one, then we return false. I mean, that's what I did here. That's all of these base cases. Okay. And then I AND the results for result 1 and result 2. Well, interesting. So this is a case for Copilot. Where is my mistake? If P, if Q. Well, what? Are meant to check if one node is none and not the other. But as written, they'll return false even when both nodes are valid. Oh, if not P or not Q. Okay. Oh, that's just because of the dumb self. Okay. Now let's see if it works. Okay. Then submit it, make sure that we're all good. Okay, so I think it was not a problem with my understanding. It was kind of just a syntactic thing, or not a syntactic thing, but I need to remember, like, when I'm checking if a node exists, it's the not of it, right? Okay. So now I'm gonna be moving over, and so we did an easy, and that was just to kind of understand the lay of the land of the tree world. Okay. Let's now go and do a medium. So unique binary tree 2. Oh, I don't like that 2 right there. I don't like that 2. Unique binary trees, this one. Okay. All right, so now we're doing a problem and it didn't even have a check mark. So this means I've never seen it. So I'm going to write down number 96. 96 unique binary search trees. Unique binary search trees. Okay. So given an integer n, return the number of structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. Okay, so first thing is, like, what is this question even asking? So I'm going to make some observations and just speak them out loud. First thing that I see is we have more of these, like, nodes that have children, okay, right? So if you start up here, I was getting confused because I was starting down here. But if you start here, I have a right child and then a left child, okay? So that's very similar to the problem that we just saw. So trees have this structure, that they have a node and that they have pointers that connect them between. Okay, so this is the structure of the data structure. Now I'm wondering, what are the type of questions which can be asked of me in this realm of trees? Well, the first time I was asked to see if two trees were the same. Okay, well, that's one type of thing. It's a comparison. Okay. Now what am I being asked? And I don't quite even know what I'm being asked right now. Given an integer n, okay, so I'm given this number, return the number of structurally unique binary search trees, okay, which has exactly n nodes of unique values from 1 to n. So the other thing that I'm noticing is I'm not even given a tree, right? I'm given n, which is an integer. And now they're asking me how many trees I can create from it. 1 to n. So 1, 3, 2, 1, 2, 3. So like all of the different combinations that I'm able to do. So now what I'm going to try is, again, go straight to the solution. But I'm going to see, is this even a problem that I should be caring about? Because if this is kind of like combinatorics or something, well, okay, that's something slightly different. So let's go to the solutions and see how they're doing it. Dynamic programming. We're not doing dynamic programming. That's not what we're doing. Counting nodes left and right. So this seems like dynamic programming. This isn't what we're learning right now. Dynamic programming is down here. We're trying to learn trees, not something else. Binary tree level order traversal. Okay, this seems a little bit better. So this is a method of traversing a tree. So now we have trees and we're able to traverse it in some fashion. Okay, well, let's investigate. And I'm trying to figure out for a tree, for different traversal methods, okay, what is the result? Like, I need to be able to intuitively understand, oh, an in-order traversal is going to look like this. A level order traversal is going to look like this. So I'm gonna write that down. I need to focus on understanding how traversing trees will result in a different like, what do I call that? Like, will result in a different scheme. Like what it looks like when I what the output is going to look like. I need to be able to intuitively feel it. So I want to be able to, I guess normally I would be writing this down, but it's kind of difficult to write and say it as I'm writing it down. So I'll just say it. So what I'm trying to do is I'm trying to get it to the point that when I see that, oh, this is in order or level order or post order, I kind of know what that means. Instead of just saying like, oh, in order is whatever it is, like process, no, whatever, process, left, right, and then the other one is left, process, right, then the other one, left, right, process. Instead of not just memorizing that, because I can map them. Oh, level order is this, post order is that. But like, what does it mean? If I should be able to look at a tree and be able to determine like, okay, well, this is what post order is going to look like. This is what pre-order is going to look like. And then what if I actually want to like, uh, how can I get a good feeling of how to traverse it in any way that I want? What if I don't want to go to the left first? What if I want to go to the right first? How is all that going to work out? So, given the root of a binary tree, return the level order traversal of its nodes. Okay. Values. So from left to right, level by level. Okay, so I think what this is meaning is level order is I start at the top, I process this node, okay, and then I process this node down its child, the left child first, but then I process its right child, and then I pop back over here and then process its left child. So how am I going to do that? I mean, the thing that immediately jumps out at me is kind of like a stack, right? Like, how am I gonna fit that in? So let's see, my stack is equal to, is that a key? No, it's not even a key. I guess I'm just gonna do a list. Okay, so need to review how to create stacks in Python. Okay. Then I know I have push and pop. Okay, so I'm gonna try like my stack dot whatever, push and then root. Okay. I'm gonna just okay, well, actually, let me come here. How do I create and use a stack in Python? Okay, so let's, so the observation that I'm making right now is that I'm given a tree and I think I can use a stack. So a stack is a valid, I don't know, maybe I'm wrong. I'm gonna actually save that until I get the problem correct. But if it is true, then stack is a valid method of traversing a tree. So you don't only need recursion. I don't know if that's true, but we're gonna figure that out. Okay. List, and then I can append, and then pop. Append the root, okay. Can I do like peak? Oh, it's just the -1. Okay, so I need to, stacks are another thing that I need to drill down on. I'm realizing that stacks are another thing that I need to drill down on when I append a value or item, when I append an item to my list, does it appear at the start or end of the list. I think append will be at the end, right? And so we have stacks and queues. Okay, so stacks and queues. Maybe I actually want a queue in this case, right? So a stack is going to process, or is going to give me back, it's what first in, there's first in, first out, and then there's first in, last out, or okay, which one is which? So Q, the first that comes in is going to be the first that goes out. So first in, first out is Q. Okay. Stack is last in, first out. Last in, first out. Okay. And now what I want to do is I want to process a node. So I want to look at a node, okay? And then I want to do the last one that I just saw, right? So I want to do the top, okay? And then I add, no. I think I want a queue because I want to add the left and the right, but then I want to process the left, then the right. Yeah, so I want to do the one that is like in its order, right? Okay, so now this kind of goes more into, well, how am I using this list? So the append is going to be putting to the last. Okay, what about a queue? What about a queue? Okay. So I can use this thing here. Yeah, why not a list? You can use a list like this. So I append 1, and then I pop, but this is O of n. Shifts all the elements. Okay, so there are two different structures or methods in Python. For dealing with queues and stacks. Okay. Stacks are with lists. Stacks are with lists. And queues are with this strange, like, the, this Q is like with this strange thing. I don't even know what I can call this. Like this strange item in Python collections. So am I gonna have to like memorize this DQ? Like, what does DQ mean? It's just something that I need to memorize? I don't know. So my Q, I'm just gonna call it like that, equals, so like this? I don't like that at all. And then now I need to memorize that this DQ has, okay, this pop left item. So I don't like this, that I need to just remember this, because I'm not going to remember this. But I also can't keep this like, yeah, I really, I'm not a fan of this, but I don't think that there's any other way. So I need to try to convince myself why a queue won't work. So why a list won't work for a queue. Why won't a list work for a queue? So now what I'm going to do is try to think about why a list won't work in the context of a queue, and that will give me a hint. That way next time I can figure out which one is which, right? Like, let's say I have a stack and I want to implement a stack. Well, do I use a list or do I use that weird one? Meaning this queue, right? If I understand that a queue can't be a list and why it can't be a list, then it can end it, like, I should be able to figure out for myself next time, if I get a stack, oh, okay, stack is the safe one. That's the one that you can use a list for. So let's think about, so a queue is an array, okay? Or in the context of a list, I have an array and I'm trying to implement a queue with it. So if I have a list or an array and then there's nothing in it, I add an element and then I add another element and then I process this first element, it goes away, right? And now I need to shift everything in my array over by one. I see, that's why. Although I should be able to maybe keep a pointer that has like start and end, right? And then as I add an element, I move my end pointer over. And then as I take away from the queue, I move my start pointer over. So I actually think that you can implement a queue with an array, with a list, but you need like 2 pointers. Okay. So I'm going to ask, is it possible to perform a queue with the list method and still have the O of 1 time complexity if I use 2 pointers? Okay, so yes, I can. Yeah. Over time, the list will grow in memory even though you're not using the earlier elements. To fix that, you can occasionally clean up. Okay. Okay, so now I have realized, like, okay, well, that's why you have to use this weird dequeue when implementing a queue. Okay. Now, I haven't satisfied my curiosity about the stack. So when I'm implementing a stack, append adds to the last element of that list. So it's just like if I have a list which has elements 1, 2, 3, 4, 5, and then I append 6, it's going to append 6 at the end. It's not going to append it at the front. Okay, and then pop will just take it from the end. Okay, so pop takes it from the end. Okay. So now with this weird one, I have the append. Pop left. Removes and returns the front element. Okay. The front element, that's what I want, right? Like pop left. And then I want to add to the back of the queue. Yeah, I want to add to the back and I want to pop from the front. Whereas a stack, I want to add to the back and pop from the back. Okay. So that's the difference between, and I'm going to write that down. So stack is add to the back and pop from the back. Okay, queue is add to the back and pop from the front. Okay. So now, how am I going to remember this pop left? So I have this, and now I want to enqueue it, right? So my queue. Oops. My queue dot append, and this should go to the end, which right now there's nothing in it, so it's just empty. I want to append the root. So now, while not my no, while my queue, so while I do have something in my little queue, I want to do what? I want to add that element's left and right. So I want to start with the left. So my queue dot append I need to get the element. So node is equal to, so I'm just going to say current node is equal to my queue dot pop left. Okay. If current node dot left, so I want to check if there's a left child. If there is, I want to add that. Now, if current node dot right, I want to add the right. Okay. It wants a list of lists. Now, how am I going to keep track of what level I'm on? So that's another thing. So here we go. In this problem, it indicates that it's possible to keep track of the level that you're on. It indicates that it is possible to keep track of the level that you are on. Okay, so if I ever come into a situation where I need to keep track of what level I'm on, I can try to figure out how this is done. So I don't feel like I'm on the right track. Straight to the solution. Okay. Breadth first search. Okay. So if not root, return nothing. Okay. So I'm creating this queue, okay, similar to what I was thinking, and then levels. Temp, okay, while queue, do that pop left. If there is a node, we append it. If there's a right, we append it. If not queue, what? If not queue. If template, what? Okay. So all of these are using a queue. Okay. And then each time we come in linked queue. Okay, so we're going to go through all of the elements in the queue. But then when we add more elements to that queue, we don't process those yet. Okay. Which is why we're able to say, okay, we processed that one level, and then we got all of the ones on the level down, but we haven't processed those one level down yet. Okay. So I'm going to try to understand this right here. I'm going to try to understand it. Okay. And then I am going to try to burn this into my head, and then I'm going to try to figure out how do I intuitively feel it, and then I'm going to think about it as much as I can. So this is how I'm trying to go about learning the Leetcode. Is just, this is the coffee one, although it's almost 11 o'clock. It's 11 o'clock at night and we're still here at the office. Okay. I didn't realize that it was that late. We should probably get going home. Anyways, so good thing Amazon is open 24/7. Okay. And then Susie works she's crazy hardworking. So she's, I don't know if she wants to head home or what's up, but anyways. Yeah, so let's try to, I am going to go like this right here. And then I'm going to try to copy or just do it from memory. So my Q is, I'm just going to call it Q, is equal to Q, okay? And then I want to do Q dot append, and then I want to append the root, okay? But if root doesn't exist, so if not root, then I want to return just an empty string or an empty list, okay? So now, while Q, so while there's still something in there, level is equal to a list. So this is going to be my result, right? No, so result is equal to this, and then each level I'm going to be building out. So for item in queue, but I remember it was range length queue, but And I can't just do for item in queue because I'm going to be changing queue as I move through things, right? So this evaluates to a static number, that length, and then just doesn't dynamically change, I think. So q.popleft is current is here. So I want to level.append current, okay? Then I want to, so I just processed it. Now I want to add the left and the right children. So if current dot left q dot append current left, okay. Then if current dot right, same thing. Okay, I think it's something like that. I took it away. Return results. So then at the end of this, we got over that level. So I want to do level dot up, no, result dot append, and I want to append the level. Then I'm going to create a new level there. I don't know if this is correct. Okay. So dot val. Okay. So this is the correct way of doing it. I need to kind of digest how this happened. I need to understand, and I need to go over, and I need to convince myself that, okay, yeah, that I'm creating a new level, and then this is going to actually go through just the ones that are currently in my queue, and I'm adding only the layer below it, right? So I'm going to be thinking about this problem for a little while, right? This is going to be not just a one-time thing. I'm going to be thinking about this. Okay, so how do I digest this information? Like, I was able to get the problem. I am able to traverse a tree with a queue. Okay. I can also keep track of what level I am on because I processed all of the nodes in my queue, all of the nodes in my queue at the same time. In one go. And that corresponds to processing the entire level. And that corresponds to processing the entire level. So I know that it's true, and I how do I describe that? Like, I know it's true, and I'm convinced of it, but I don't feel it, if that kind of makes sense. So, like, I have my node. Okay. I have my node, and then I'm adding the stuff underneath it in my queue. So I have my node, and I add the left, and I add the right. And that's its children. And then I go down to, and then I do another. Now I have two in the queue. Okay. So then I come back up through that while loop. Okay, great, good. That's a new level, right? Yeah, it is. Because I only processed that one, which was the root. And the length was 1 at that point, right? So now I have 2 in my queue. And it's a new level and new parentheses. Okay. So then length is 2, so in range of 2. So I'm going to do this 2 times. What am I doing 2 times? I am going and I'm appending, right? Am I appending? No. Wait, yes, I am. I'm hopping. I'm hopping from the top. So I'm taking 2 things out of the queue. Because at the very beginning at the very beginning I said that there was 2 things in my list, which represents the 2 nodes, the 2 children nodes. Okay? And then I'm going to take one thing from the top and take another thing from the top, or from the beginning, right? And I don't care about the other stuff that I add to it, because that's just I'm going to add more stuff to it, but I'm only doing in range 2, which is taking here, and the first 2 elements are not going to, I'm not inserting anything above. So that's why I'm able to, I'm changing my list, my queue, but I'm adding to the back, so it's fine. And then I take from the front, and then I take from the front again. So I'm just doing 2 takes from the front. Okay, so the left child, and then the right child, but then each child I add 2 more elements, right to the back though. So the left child's left child, then the left child's right child now are at the back. And then the right child's left child and the right child's right child is at the back again. So now I have 4 elements here, but I took from here and then I took from here, and now there's 4. So in range of 4, and that's a new level. Okay, so because this is fixed, I'm only taking out how many are in that specific level. Okay? I don't even do anything with item, I'm realizing. So what I'm going to do now is I'm going to let my brain simmer on this a little bit, I think. And then maybe I'm going to come here and I'm going to go like this, and then I'm going to come back to this problem in a couple hours, or maybe tomorrow, or I don't know when, but I'm going to come back to it very soon and try to do it again and convince myself of it more. And I found this kind of learn and forget method is really helpful, that I'm able to do a problem, try to understand it as much as I can right now, okay, then forget it a little bit, and then come back to it. And when I come back to it, I might have forgotten it, but then I learn it again and try to find, okay, where am I tripping up? So I come back to it maybe tomorrow. I might not remember. I might get something wrong. But then that area of, oh, I got this wrong. I couldn't remember how to do this specific thing. Well, that actually shines a very good light on, hey, you're not too comfortable with this particular concept, or this is where you are struggling. This is where you're not quite understanding something. And then I can dig more into it. So that's how I'm going to go into this. Okay. And then once I feel and I understand and I intuit this problem, then we're going to continue to do other problems. But I'm not moving, right? This is kind of the difference between what I used to do and what I'm doing now. Is what I used to do was, I would just do a problem. If I didn't, and I wouldn't even look at the answer. I would try to do it, and then make myself like feel really stupid, because I would just be like, man, I'm just so dumb. I can't do these problems. Why am I? And then I would lower my morale, right? And I would feel bad about myself. And then I would, okay, fine, go look at the answer. I wouldn't even really, you can go watch my old videos, right? When I was doing Leetcode, I wouldn't even look at the answer. I would just, okay, fine, here's the answer, but whatever. How is it working? I don't know. Anyways, and then the next day I would do it again. No wonder I didn't learn anything, right? So now I'm completely flipping that, and I'm focusing on the answer. It's okay. Like, if I'm struggling during the, like, thinking of the answer, well, then just jump right to the answer and understand the answer, right? So this is kind of how I'm completely changing my methodology from, as you saw in the past, the way I was doing it, to now. This is the way that I'm moving forward, and this is the methodology that I'm trying to learn. So yeah, I'm going to continue to try to do this problem. I'm going to try to understand this problem. I'm going to keep on it. I'm going to keep thinking about this problem. I'm going to play with those concepts of, okay, well, level 1, level 2, level 3, and how that interacts with a queue. Okay, queues are able to traverse these trees, and then I can process all of the nodes within my current length, and that length is how much the start of the level is how much children I have of that branch of children which are currently in my queue. So I need to keep thinking about this, and then do it again. Get to the, see where my stumbling blocks are again tomorrow. And then once I feel confident in this problem, move on to the next problem. And then when I move on to the next problem here, I'm going to do the exact same thing, but now I'm going to try to find the connections between this one right here, this problem, this 102, and I don't know, maybe 105. Like, maybe I do this one next and say, okay, well, what are the differences? What are the similarities? Is it the same data structure? Is it the same traversal? Like, am I using queues? Am I using stacks? Am I using like recursion? Like, What are the differences? Why would I use recursion one time and a stack another time? Why would I use this in one instance and that in the other instance? Why would I what are the different traversal, right? Like trying to make as many connections. Not only right now I'm just doing one problem, but okay, once I go and get to a new problem, okay, we'll understand that new problem, but then also understand kind of what are the connections between the problems, right? Like I did one problem and I do another problem. What are the different, like they are both trees. Well, how are they connecting? Like what's the connection? Like how are they similar? How are they different? What did I learn from one? And what did I learn from another? And how does it generalize into this idea of tree? Okay, and then if I'm given a problem, and how do I identify that it's a tree problem? Now, actually, that question is really easy because I think if you see a problem, it essentially tells you that it's a tree. But something like two pointers or sliding window or any of these binary search, right? Like if we come here, like binary search, sliding window, two pointers, all of these ones are tricky because you don't know. You don't know if you're given a problem, and a lot of times it's difficult to even find out, like, oh, well, I should have used the two pointer method, right? So abstracting out, like, okay, well, what are the connections between it? How would I have known what problem or what method to apply? How would I know that it's this type of problem? That's kind of what I'm trying to do. All right. Anyways, thank you guys so much for watching this video. If you enjoy this kind of video and want to watch more, subscribe, and we will continue on our journey of the Leetcoding, right? And also the project videos where I am doing a whole bunch of projects with the hope of being able to learn a lot of those concepts to teach myself how to become a software engineer. So that's kind of what I'm trying to do with this channel right now. If that is interesting to you, subscribe. I would love to have you along on this journey. I hope you have a wonderful rest of the day. My name is Timothy Lee Grant, and see you tomorrow.